Hello friends, welcome back for another deep learning image classification project, Pneumonia Detector. The Pneumonia Detector is a deep learning model which takes X-ray images of lungs of a patient and it detects whether the patient is pneumonic or normal. So let's start how to do this model. At first, I want to say that I am using Kaggle notebook. Make sure that you should change the accelerator to GPU T4. Okay, then at first I have imported required libraries like NumPy, Pandas, Tensorflow, Keras, Matplotlib. From Keras I have imported layers, and from Matplotlib I have imported pyplots. So let's run this cell. NumPy is for numerical calculation, Pandas is for data manipulation, TensorFlow, Keras are used for building the model, and Matplotlib is to show or visualize the data. Yes, session is started. You can see here we have HDD, CPU, RAM, GPU, 2 GPUs. Okay, after that I have created GPU strategy. So to create a GPU strategy we have to specify this tf.distribute.mirror strategy. So this mirror strategy will create a GPU strategy and which we can use for model training with the GPU accelerator. To see the number of replicas the GPU has, you can apply the attribute num replicas in sync to the GPU strategy variable. So let's run this. You can see number of replicas equals to 2. So we have 2 GPUs which are our accelerator for this project. Then I have created some parameters which will be used later in our project, like auto tune, batch size, image size, class names and buffer size. Let's run this cell. Successfully we have created these parameters. Then I have downloaded and converted the dataset into TF record datasets. So this is the location where the images are available, and this is the path where levels are located. So using TF record dataset method, I'm downloading and saving that in train images and train paths. After that I am zipping both train images and train paths and creating a dataset out of that. So let's run this cell and create the dataset. So dataset is created successfully, and here in next cell I am counting the number of normal images and number of mnemonic images. For that I am iterating over all the file names available in train path, and if the file name contains normal in it, then I am appending that in a list, and at last after all file paths I am taking out the length of the list, and saving that in these two variables. So if normal is present in the file path, the list will be appended by the file name, and if pneumonia is present in the file path, then pneumonia will be appended to another list, and the length of the lists are saved to these variables: normal image counts and mnemonic image counts. And let's see the number of normal images and number of pneumonia images. Let's execute this cell. So you can see we have 1349 normal images and 3883 mnemonic images. So as the mnemonic images are higher than normal images, that's why we have to introduce class weights, because the data is imbalanced, and when we consider to use CNN model or CNN architectural network, then we should provide balanced data. If we provide balanced data to the CNN, it will give us better accuracy on validation set. That's why we have to introduce the class weights. So in next step, I have created class weights for level 0 and level 1. At first, I have added both the counts and saved in the train images count, that is total images in the training set. And for weight for the level 0, I am dividing total images divided by normal images divided by 2. For the level 1, total images divided by pneumonia images divided by 2. After that, I am creating a dictionary where keys are the levels and values are the weights for the levels. After that, I am printing both weights. Let's run. So here you can see weight for level 0 is 1.93 and something, and weight for level 1 is 0.67. So here you can see we are considering pneumonia images level equal to 1 and normal image level equal to 0. So as we have less number of normal images, that's why we are introducing a higher weight value to it. And for pneumonia images, as we have more number of images, that's why we are introducing a lower value than the weight of level 0. After that, I am pre-processing. For pre-processing, I am using preprocessor method, and in preprocessor method I am passing two parameters. One is image, the raw image, another is path, the raw path. From path we will find out the level, and from image we will find out the resized image. So for image case, at first I am decoding the image with 3 channels, and then I am resizing the image with the above mentioned image size. And for path, I am splitting it into a list of strings and saving that in a variable parts. And if the penultimate value in the list parts if equals to pneumonia, then I am saving 1 in the variable level, else I am saving 0 in the variable level. Then I am returning image and label from the method preprocessor. So using the map method applied to the dataset and passing the function preprocessor to it, we are doing preprocessing to whole data set. Then I also passed an argument number parallel calls equal to auto tune. So parallelly data will be pre-processed when we set this argument. Let's run and pre-process our data set. So yes, the data set is successfully pre-processed. After that, I am splitting the data into trained DS and well DS. Before splitting, I am shuffling the data set with the specified buffer size, and the buffer size is nothing but 10,000, I think, as mentioned earlier. And as we have around 5200 plus images with us in the data set, that's why we are taking 4200 images for training and remaining for validation. So having the train size equal to 4200 and passing that to the take method applied to the dataset, we are getting training dataset, and skipping that from the dataset we are getting validation dataset. So let's build train DS and well DS. Yes, we are successful in building train DS and well DS. Let's move forward. So let's check what is the shape of image and what is level. As the dataset is not batched yet, so we have to get, or we will get, a tuple of 3 elements for image case, and also it should print a level value either 0 or 1. Let's run this. So wait for a while, it is taking some more time. Yes, you can see images are resized to 180, 180, 3. The 3 is nothing but the number of channels the image has. So the level is 1. Yes. After that, we are caching, batching and prefetching the data set. So for train DS, we are caching, batching with the batch size 64 as mentioned earlier, then prefetching with the buffer size auto tune. So the data will be prefetched immediately when the model is training for next iteration. So as we have less than 10,000 examples in our data sets, that's why we will consider it as mini dataset. And for mini dataset, if we cache it, then the dataset will be saved in the RAM so that the memory can be fetched quickly by our model. You have more than 10,000 examples, then don't cache. Your memory utilization will be maximized and you will face troubles. So applying case batch preface method to both train DS and valid DS. Let's run it and save in the existing variables. Okay, it's done. After doing all pre-processing steps, I am visualizing the data. So from the train DS, I am taking out one batch and splitting the batch into image batch and label batch. After that, I am iterating over 25 elements from both the batches and selecting a subplot for each image or label. Then using the plt.imshow method, I am showing the image. Before showing, I am rescaling the image, and if the label batch of I is true, I hope you will understand, because label batch of I will result into either 0 or 1. So 1 means pneumonia, and if case 1 is a true value and 0 is a false value. So if this case is true, then we are giving title pneumonia, and if the case is false, then we are giving a title normal to the image. Then we are removing the excesses from the images. So we are doing this for 25 images. After that, we are showing the whole plot. Let's run this. So it will take some few seconds. Wait few seconds, it will come. Yes, we got. So you can see many images are showing pneumonia and few images are showing normal. After that, I am building the CNN. In CNN model or network, we will have two main blocks, convolution block and dense block. For that, I have created two blocks defining these functions. So in convolution block, we will have two separable convolution layers, then base normalization and max pooling layer. And in dense block, we will have one dense layer, one batch normalization layer, and finally we will have dropout layer. For creating these blocks, we have to pass filters and inputs to the convolution block, and we need to pass units, dropout rate and inputs to dense block. Let's run this. Yes, it is done. Then using a method build model, we are going to create the model. At first, we are selecting the input function from this Keras and passing the shape of image. So you should remember one thing, that whenever you are passing a shape, you should never include the batch size. So only you have to pass the shape of the image. After that, we have a rescaling layer to reduce the computation. And then we have two standard convolution layers with 16 filters and 3 kernel size and ReLU activation and some paddings. Then we have a max pooling layer. After that, we have 3 convolution blocks with different filter numbers, and then a dropout layer with drop rate 0.2. Then again we have a convolution block with 256 number of filters, and again we have a dropout layer with 0.2 the dropout rate. Then we are flattening the whole output. After that, we have 3 dense blocks with different number of units, different dropout rates. So in first block we are providing 512 number of units and 0.7 as dropout rate. Then in second dense block we are providing 128 units and 0.5 dropout rate. Then in third block we are providing 64 units and 0.3 dropout rate. Then at last we have a classification layer, that is a dense layer with 1 unit and sigmoid activation function. So to create a model, we have to call this functional API or model class from the Keras, and we have to pass 2 things. One is inputs, another is outputs. Inputs is nothing but the images, and outputs is nothing but the dense layers output, and saving that in the variable model and returning that. So let's run this and create the method build model. After that, we are building and compiling the model. One thing I want to say that whenever you are creating a model and compiling a model, and if you are using accelerators for training purpose, then you have to create the model and compile the model under the scope of the strategy that you are using. So with GPU strategy.scope, I am building the model and compiling the model. And I also want to say a note to you that the optimizer laws and metrics which you are going to use in the model compilation, you should create that under the GPU strategy or TPU strategy that you want to use. So in my case, I am using 3 metrics. One is binary accuracy, another is precision, and the last one is recall. Then I am using a learning rate scheduler because too high learning rate will cause the model to diverge, and too small learning rate will cause the model to be slow. So to avoid that, I am using the exponential decay scheduler which schedules our learning rate and then passing the optimizer laws and metrics in the compilation of model. So let's run this and build and compile our model. So it will take. So the model is built and compiled successfully. Let's go for training. Before training, I have created two callbacks, checkpoints and early stopping, and the checkpoint callback saves the weights of the model. So next time if we want to use the model, we do not have to spend a time training it. In the checkpoint, I am monitoring validation binary accuracy, and that is to be maximum, and passed an argument save best only equal to true, so that the checkpoint will save the best weights of the model. Then we have another callback, early stopping. The early stopping callback stops the training process when the model starts becoming stagnant or even worse. So here also I am monitoring validation binary accuracy with mode max, and we are giving patience equal to 10. That means if the maximum validation accuracy is not increasing or stagnant in the same value, the early stopping callback will have a patience for 10 epochs, and if it is not increasing, then the callback will stops training the model. And when we pass the argument restore best to weights equal to true, then it saves and restores the best weights even if the model became worst after many iterations. And you will understand better when this training starts. So in fit method, I am passing train ds number of epochs, that is 30. You can go for a range between 25 to 100. And for validation data, I am passing val ds and passing the class weights and also passing the callbacks. Let's run this and train our model. So it will take a few seconds before starting. Yes, the first epoch will be started very soon. If the training accuracy is greater than the validation accuracy, that means the model is overfitting, and if the training accuracy is not above 60, that means the model is underfitting. So here you can see the training accuracy is 70% and loss is 62%, precision is 87% and recall is 69%. The recall is nothing but the probability of correct predictions out of all true cases, and the precision is nothing but the correct predictions out of all positive predictions. Yes, the first epoch is completed. So after 17th epoch, the model stopped training because of early stop. Because the validation binary accuracy is not increasing. Let's see the best validation accuracy. Here you can see 95, 0.95, the best one. So after that it continued for 10 epochs, 1 2 3 4 5 6 7 8 9 and 10. The validation accuracy is not increased, that's why it stopped the training. And let's see whether it restores the best weights or not. For that, let's evaluate the model with validation dataset. So you can see the binary accuracy now became 0.95, that means 95%, which is the one I shown just now, that is this one, 7th epoch. And we have precision equal to 100%, that means all the mnemonic images are accurately classified into mnemonic, but the recall is 0.93, that means some normal images are also classified into mnemonic. Let's evaluate our model on unseen data, that is test images. So again I am using TF record dataset to download the images, and then I am creating the dataset test.ds. After that, mapping the preprocessor and batching the test.ds and evaluating the model. Let's see this. I already mentioned here that the binary accuracy is 80, 0.80, and loss is 0.80, precision is 0.76, and recall is 0.96. That means here you can read, we see that our binary accuracy on our test data is lower than the binary accuracy for our validation set. Yes or no? Yes, we have 0.95 here and 0.80 here. This means overfitting. Then read it. Our recall is greater than our precision. Yes, our recall is greater than our precision. It means that almost all pneumonia images are correctly identified, but some normal images are falsely identified. I already told that, and we should aim to increase our precision. Okay, that's fine. After all, I am saving the model. So model is saved successfully and the first part is completed successfully. And to download the model, you go and click on the expand sidebar. After that, go to the output section and go to this directory. You can download the model from this directory. Yes, model Keras. Then click on these three dots and here you get download. So download it and use the model. Thank you. Let's start the second part of Pneumonia Detector. So here we will create a user interface using Streamlit. For that I am importing Streamlit, Pandas, NumPy, Tensorflow and PIL. So Streamlit is for building the user interface, Pandas is for data manipulation, NumPy is for numerical calculation. Even though I am not using these libraries, it will be used internally. So better you should always import these two libraries. Then importing TensorFlow and Keras for TensorFlow operations and reloading the model, and importing PIL. PIL is used to read the image uploaded by the user. So then I am reloading the model where passing this file path to the load model method and saving the model in the model variable, then creating the interface. At the first I have a title. For that I have created a container, and inside that container we have two columns with different width sizes and vertical alignment equal to center. This means that the content inside the columns will start from the center. Then we have image, that is a logo under the image column with a width of 150 pixels. Then we have two write methods showing Pneumonia Detector, one as title and a description of the model in the another method under the heading call. After that we have another container for input and output. At first we have a file uploader where you have to upload X-ray image of lungs, and it can accept only one file. That's why I have created accept multiple files equal to false. And if the image is uploaded, then I am creating two columns, one for input, another for output, without any borders. Then under the input column I am showing the image uploaded by the user, and under the output column at first I am reading the image using open method applied to image module of PIL, then resizing the image to 180, 180 because I have used resized images during training. Then expanding the dimensions so as to increase the shape and add batch. Then passing that image to the predict method applied to the model, and if the prediction is less than 0.5 I am returning this image, that is normal.jpg. It's a image, or if you want to say I can show that normal image is this, the lungs are normal, and pneumonia image is this, the lungs are pneumonic, go for medication. After that I have created a container for sharing the contents, and three columns I have created, one for YouTube, another for LinkedIn, another is for Hugging Face. In YouTube you will find the explanation of all the codes and material. In LinkedIn you can connect with me, and in Hugging Face you will get the deployed code and the application. So under these calls I have created link buttons, and in the link buttons I have passed the labels for each button, then an icon for each button, then an URL for each button, then I have used use container width equal to true so that the length should be equal for each button, and then I have given a help section for helping the users. So to run this file and see the output, we have to go for terminal, and to open the terminal in the VS Code, press Ctrl Tilt and clear all with the command clear and enter, and go to the directory where the file is present. In my case the file is present in Pneumonia directory and I am at Pneumonia directory, so I don't need to change the directory. And to run the file, enter streamlit run and the name of the file, that is app.py, and press enter. So yes, it is taking some time, wait a while. The file is running with the variables that we have created. Yeah, this is the user interface where the name is this Pneumonia Detector, and here we have to drag and drop or upload the file, and this is the YouTube section, this is the LinkedIn section, and this is the Hugging Face section. Let's go to the new tab and find out some X-ray images of lungs of both pneumonia and normal cases. So pneumonia lungs X-ray images. So here you can see, let's minimize this. Here you can see, let's go to images. So this is a pneumonia image, so let's drag and drop there, dragging here. Yeah, we got the lungs are pneumonic for medication. Here also see that chest X-ray showing pneumonia, that means it's a pneumonia image. You can go for another image. Let's go with this image, drag and drop here. Yeah, the lungs are pneumonic, go for medication, again showing the same. So let's change image to a normal one. So normal chest X-rays. Go to images and let's before that wait a while. Let's go for this normal chest X-ray, drag and drop here. You can see the lungs are normal, and let's change it for another image. Let's go and drag and drop this image. Again you see the lungs are normal. So this is the best case. You can see So thank you.